So hopefully you also got a good score when running your CNN on all the data. 98.5% is very good. We're going to see if we can do a little better. What I want you to do is copy the previous notebook. So go to File, save a copy in Drive, and then let's call this one just MNIST Okay, what I want to do right now is I want to make some modifications to the convolutional neural network, but I want to do it using what we've already learned, okay? Along with a couple other pieces that apply generally to neural networks. So let's go back and add in a limited number of rows so that we can, basically go through it quickly. Okay, that's the whole point before adding in all the data at the end. And I think we can go straight down to the CNN, and in particular, the CNN model right here where we started. So go ahead and runtime run before, and let's look at what we can add in. And I want to start with something simple, which is batch size, right? We haven't done batch size. And it's been mentioned before, but the idea behind batch size is that it's basically the number of parameters that are pushed through the neural network at a time before making updates. And if you've got 2,000, like how many do you want to go through at a time before updating? The default is 1. I don't know, 64 seems reasonable to me. You could pick something different. And let's see what kind of a change that makes in itself. I want to look at it's not just about making changes, it's also about looking at, hey, what type of change does this make? Now, this wasn't actually used on this data set, okay? This was used on the previous one with the full data set. So maybe we actually do verify, is it really a batch size of 1? And see what we change it to 64 does. Okay. So you can see there's 8,954 parameters, right? And we've got the max pooling CD, 2D, cutting down the number of parameters by half. Then another convolution. Note that the second convolution has a lot more parameters because it's based on the first one. It's coming out of something that's multi-dimensional here. And it does seem like it's going a little bit more slowly. I read that the default batch size is 1, but maybe that I would, based on this, I would say maybe that's not in fact true. Let's let that run and then prepare to add in some other pieces here. One of them also that we use is early stopping. So recall that also needs to be imported, and it's from keras.callbacks import early stopping. That way we're not limited by this arbitrary 20, 50, whatever number of epochs that we're choosing. This allows us to optimize the number of epochs. Yeah, it's definitely taking some time here. So why, right? Because it's going one parameter at a time. They must have changed the defaults. That's why experimentation is always good here. You might be able to read things, but how do you know if the reading is as updated as the code that you're running? Or, sometimes it actually goes in the other direction where it could be the case that your code is based on like a previous version and maybe isn't as updated. Okay, well, how do we add in the early stopping? Call it the early stopping monitor. So for instance, early stopping monitor, I'm giving the variable name here, and then you're setting it equal to early stopping, right? With the patience. And the patience, recall, is that how many rounds do you want it to go through before it actually says, you know what, I'm not seeing any improvement here, I'm going to stop. I don't know, for this data this size, maybe 10. I'll go bigger or smaller. I just want to see how does this do with the batch size of 1. Oh my gosh, look at that. It actually did better. Very interesting, right? So I think the default may be something like 64. So that's interesting, right? Let's let's play around with this a little, okay? The batch size. Like, let's try something just different, like 32, and see what do we get. Okay, and note that and that was the first model that we ran. I always like to check, like, is it restarting? When you define sequential here, it is initializing a new model each round, okay? You can try to like add layers like after the fact, and you can keep going. Okay, so batch size is clearly playing a role here. Okay, we got an error. Let's see, what is the error? No module named keras. Okay. Go up to where, yeah, keras it should be, of course. Okay, so note here that's just importing and defining the early stopping. We're not using it yet, okay? We just define it, but when we're fitting it, we're not using it yet, okay? What we actually need to do is set the callbacks equal to the early stopping monitor. I think it's a list, by the way. We put early stopping monitor in the list. Okay, another piece that we used before that we could just go ahead and add in is the validation split. So that way we can see how the testing is going each round. So the validation split, and the early stopping uses that. It doesn't use the training. It uses the validation split. Say 0.2 is standard. Okay, so how did it do when we change? I was eager to see what does the change make. Well, if we go down, not nearly as strong. So this is really interesting with the batch size making a big difference. Okay, what I'm going to try to do is drop the batch size. But note also we've got this early stopping monitor in play now. And what it's going to do, instead of like, we don't want to set epochs as 20 now. We want like at least like say 200, you know. You can do it higher because it's just going to shut down when it doesn't see an improvement over 10 rounds. Okay, and again, this is all stuff that we've done before, but as you can see, they can be used for significant gains in convolutional neural networks because these are sequential deep learning networks. All right, so let's add in the early stopping monitor, run it. And then while that's running, I want to consider a new piece here to add. It's the optimizer. So we've already got an optimizer. However, you can actually add an optimizer with an adjustable learning rate. And that's something that's really key, setting the learning rate. And I think we could talk a little bit about the learning rate. I like to think of it as how quickly the model learns, right? So, right, imagine that you have some curve, it's like a polynomial with multiple minimums and maximums. If you're trying to minimize the error, small learning rate's going to go really small intervals to try to find these errors, right? And it could take too long if it's too small to find the best one. But a big learning rate could like zigzag and miss them, okay? And the small one, by the way, can even get stuck inside one is another thing. I'll have to show you my stuck in a local optimum shirt. Okay, so how do we do that? Well, I'm always eager. Let's check the test score with 97.6. So, wow, that batch size is making a big difference. Let's just try 2. That's kind of cool too, right? How you can see once you've run the cell, you can like reset and add new things to it. Okay, so how do we get the learning rate set? What we actually need to do is add in the optimizer separately. So come up here and try from keras.optimizers. And we can try other ones too. Import atom. Okay. And then what you do, right? You go down and, well, here I've got atom. Like, how do I do that? Well, before you do that, you can set optimizer. I just call it optimizer equals its atom, but now you can pick the learning rate. Now the default should be 0.001, I believe. And then instead of setting the optimizer equal to atom like this, you set it equal to optimizer here. Now the whole point of this, right, isn't to like redefine like a default optimizer, it's to say, you know what, we can change the learning rate because different learning rates can result in different scores. Okay, let's see how we did with the batch size of 2. Better, right? 98.7, not quite the 99 that we had. And note we've also put in the validation accuracy. So These are good validation accuracy scores. You can see that the accuracy is perfect. So we're still doing a little overfitting, right? Now the learning rate isn't necessarily designed to reduce overfitting, but it can help. Okay, so I believe that that was a 0.001. Let's see what happens if we, in fact, lower it by a factor of 10. All right, press Shift Enter, run the code. With the batch size of, what is it set at 1? 2, it's going to take some time. So, and then we can try like 0, 0, 1 and some like numbers in the middle. Okay, of course there are ways to do grid searches. I always think it's nice with the deep learning to actually look at it as it goes so you can like check in on it. All right, so this should be interesting. So what other pieces haven't we added in that we added in before? One of them that I think is a nice one is, recall this, from keras dot constraints, code with me, import max norm, right? And this is what the max norm does. It's limits the influence of the weights. So you may find, like in convolutional neural network, that a particular I don't know, filter, like each round it's like scoring, you know, so it might be the case that a particular filter is given a high score and it's going to cut down on that, so it doesn't overfit, it reduces the overfitting. So we can just try it, right? We can just throw it in here in this first one, say, hey, kernel constraint, again, this is designed to reduce overfitting, equals a max norm of 3. Okay, go down, see how we did. Not so good. So the learning rate, see, when we adjusted the learning rate lower, right, what's happening is it's missing the minimum error here, right? You see the validation accuracy is not nearly as good. So that's too low, right? We could go a little higher. Whoops, sorry, I went higher, high, low. That was the default. So let's see what happens if we do another. I want to do another one, maybe without the kernel constraint. Let me show you a little technique you can try here. So this is the last one, right? I think the commas don't matter, so you could try something like this. Will this work? Right, you comment it out, and then you can quickly comment it back in. Let's see. Yeah, so it's going. So we have a different learning rate. And again, what was the change? The previous learning rate was bigger, potentially bigger jumps, potentially missing. This one could potentially get stuck in one, but it's gonna like kind of like do more searching, you could say. You can see it's starting with a low accuracy, so this one might be too low. But if you compare like the accuracy and the validation accuracy, so far they're closer. And note too that the model is learning, right? Because the whole point is, can it learn and find better parameters? And as long as it continues to learn, because we've set it for like at least 200 epochs, it could go that far, right? It's only going to stop after it sees no improvement over 10 rounds. And keep in mind, we're using a small subset of the data as well. So after we do that, we can throw in the kernel constraint max norm equals 3. And the only other piece that we did, I believe, before that we have not yet included is dropout. So let's get it set up. It's another layer. And again, you can use it to reduce overfitting. Like if you check at the very end here, like the flatten, we can say that there are, hands keep scrolling down. Was it 400? I don't know. Maybe there's like, say there's like 400 what's the right word? Is it like neurons? It's like, I think it was like nodes. There's like 400 nodes going forward, and the nodes would be like the little circles. It's like the key piece, right? Right, like the layers. I mean, the layers are like how many nodes, right? This is saying, hey, we need possibility of 10. If we start with 400, then it's saying, okay, those 400 weights, we can reduce them using dropout. So I can like add dropout layer. That would be model.add dropout, and 0.2 is a norm, meaning that each node has a 20% chance of dropping out. When there's over 400, some of them are going to drop out. And again, that's designed to reduce overfitting. So let's see, that this one took longer, 98.7. So we didn't see major gains, and note that if we look, it did end up overfitting as well. So here's what I'm going to try. I'm going to add in some of these other pieces and start getting them to work together. Okay, you can see how there's a lot to play around with. And note, I'm intentionally not working on the convolutional pieces. We'll try that another time. Right now, I just want to look at the other pieces. Like, let's add in the kernel constraint max norm equals 3. Now, the other thing is, I think you want to add it here too, because if you go down to the summary, if I scroll up in the summary, well, look, this is the one with all the highest number of parameters, okay? It's this one. So I think that's the one you definitely need it. So what the heck? Let's try it both places. And again, you can always comment it out, right? If you do it like that. It's kind of cool, right? If you do it each line like that, you can comment out any line, which can be nice. And let's try the dropout layer too. So this is a lot of regularization added in. The other thing is, I think, so the default is here, and I think I'm going to go in between actually and do 0.005. Okay, so let's see how this model does. Now we've added a lot in here. I'll just highlight the code as it's running. We have a very low batch size still. I think upping the batch size is probably a good idea. And this has to do with, like, you don't just want to fixate on, like, hey, what's the best score? Yeah, that's the goal, but you also want to try to keep things regularized. Like, that's a lot of updates that it's going through. So I think I want to increase that definitely. Maybe to even something as high as 64. Okay. I think with these other pieces involved, like, maybe it'll make a difference. Maybe not. We can do a quick check. How are we doing? Yeah, we're still having some typical discrepancy between the accuracy and the validation. It's moving a little more slowly, so we'll see what happens. Just to review, what all have we done so far? What does the code mean? I think you want to know what the code means, right? That's the key. We're very code focused, right? We're not as concerned about the math. Okay, so here are all the imports. The imports just allow us to use everything. Let's just take it one line at a time. We initialize a sequential model, meaning it's going to go left to right. That's the whole point. First piece, adding the convolutional layer, essential for a convolutional neural network. We chose 32 filters, okay? Kernel size of 3, meaning 3 by 3. So what that 3 by 3 does is it goes across the entire pixels and it narrows it down to like a smaller shape. Activation ReLU means everything's positive. Input shape is each row is 28 by 28 by 1. And kernel constraint max norm equals 3. We're saying, hey, let's apply some regularization. Let's do some preventing of overfitting. Let's penalize the biggest weights, okay? And what that does is it allows kind of like little pieces not to have too much influence, and it allows us for more generality. Okay, next. Max pool 2D. That cuts basically in half the number of, you could call them feature maps, okay? We do a second convolution on all these maps, okay, so that's a lot. We keep the kernel size at 3. This time, though, we just do like 16. Okay, so it's 16 new ones, and we're doing an activation of ReLU. Again, kernel constraint max norm equals 3, same effect. Max pool 2D, same effect. We cut it in half. Then finally, we flatten it out, and we get all these one dimensions. Now we say, well, maybe that's too many. Let's drop out 20%. And finally, we got that one-dimensional string. Let's just like look at them a pixel at a time and try to optimize fitting them into the bins of matching the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. They're one-hot encoded, and softmax is what we use for that. Then we can show the summary of the model, show like how many parameters we're using and all that. We picked Atom as our optimizer, can be changed. And we've been toying with the learning rate, how fast do we want it to learn? And what can we do to try to tweak getting better scores? Learning rate is considered one of the most important hyperparameters in neural networks. Keep that in mind. Then we compile the model, including our new optimizer. We keep our loss at categorical cross entropy and add in an accuracy metric so we can see the percentage correct. We put in an early stopping monitor so that it can just keep going until there's no improvement after patience equals 10 rounds. We fit the model to the data on X and Y. We give a max of 200 epochs just so it doesn't go on forever. Now the batch size we've been toying with, right? It was at 1 gave us the best score, then 2, and then I'm saying, well, maybe you want to do something closer to 64. You know, maybe 32 and 64, 128 when we look at all the data. The validation split shows us a scoring metric each round that's used in conjunction with the early stopping and wants to know when is the test score not improving. This implements early stopping, and finally we get a score on the test that it's never seen before. So how did the last model do? 96.3, not that great. So, you know, with all that talking, I can start to forget, well, what when we were at 99 before, like, what did I change? What didn't I change? That type of thing. At this point, have we done the kernel constraints? I think something important to look at is if you compare the accuracy to the validation. Like, accuracy is still really high at 99 and validation is still like 94.7. So we want to do some constraints here. Okay. And again, batch size should help. All right, I'm going to give this one a run. It's going to go faster. In fact, let's start with 64 to make it go even faster. Why faster? Because we're going to update the parameters after, you know, a group of 64. Okay. And you can see that here, right, how it's actually moving faster. And it can be fun to watch it too. And you can also plot these, which we can look at. Your cohort leads can show you. So we see an accuracy steadily going up. And what about the validation? Well, validation is doing fairly well. I mean, it's, you know, 98 to 96. That's not bad, right? We've seen worse, 97. So it's I think this is doing maybe a little better. What do we get at the end? 98.7, right? So you can see how these things can work in conjunction, right? You can up the batch size and, like, you know, we see some nice gains here. Is it still overfitting? It is by a little bit. Okay, but not by a lot. So that's an introduction to the different kind of general deep learning hyperparameters, you could say. Batch size, early stopping, a new one we're doing here now, the optimizer. We've got dropout, kernel constraint max norms, and you can see how they can definitely be used to give you kind of nice improvements in the data, right? I mean, we're at what was it? 98.7%. That's outstanding. So what I want to do, I want to go back to the top and I want to take it out. Okay, it's going to take a little time to run. Shouldn't be crazy, right? But try it in all the data. Just do runtime, run all, see how it does, and then we'll check back.